Yeah, so I'm going to tell you about a surgery operation that happens on RP2s embedded in S4. First, I'm going to describe the surgery operation. It's like an old idea, but you might not have come across it before. And then I'm going to give motivation for why you should actually be interested in the surgery. And then the main thing is talking about how to actually explicitly perform the surgery operation using the theory of trisections, which is a combinatorial description of four manifolds, which has sort of been gaining popularity in recent years, depending on who you ask. Okay, so the idea is we have an RP2, and it's smoothly embedded inside of a four manifold, X4, so that it has Euler number plus or minus 2. So by Euler number, I just mean you push the RP2 off of itself, and at the intersection points, you could locally orient and count with sign. And so our motivation for considering plus or minus 2 is it's just a fact. I don't even know who to attribute this to, but it's discussed in the Carter-Saito surface books, that if you have an RP2 embedded in S4, it will always have Euler number plus or minus 2. So this discussion is always going to be relevant to any RP2 embedded in S4, but it is a more general idea. Okay, so I have my surface. I'm going to call it F, which stands for surface, always. And I'm going to serger along F, by which I mean delete a tubular neighborhood and re-glue it by some automorphism of its boundary, right? So the first step of that idea is understanding what is the tubular neighborhood and what are the automorphisms of its boundary. So we can just draw explicitly tubular neighborhood of an RP2 is going to have the same 2 skeleton as an RP2. So I'll draw the one with negative Euler number. It's going to have a 1 handle and a 2 handle, which links it twice. So, I mean, this was a summer school. I don't know if everybody has seen this kind of notation before, but I really just drew what I said in words. This is a 1 handle, and this is somehow a 2 handle, which runs over it twice, just like RP2. And then, because I'm building a 4 manifold, I have to specify the framing with which I attach the handle, and that's determined by the Euler number. So I'm pretty sure this is Euler number minus 2. So it's like a fun little exercise if you're new to Kirby calculus. So that the boundary of this manifold is a Seifert fibered space with 3 singular fibers. It has a diagram that looks like this. A 0-framed 2 handle, and then 3 2 handles whose framings are 2 with some sign. And in particular, we have a preferred open book on this boundary. So this is a picture of a page. This is a sphere with 3 punctures, so it's a planar surface with 3 boundary components. Those are the bindings of the open book. And the monodromy is exactly 2 right-handed twists around these 2 boundaries and 2 left-handed twists around this boundary. So I can see the bindings of this open book or Seifert fibered structure sitting in my Kirby diagram over here. For exactly these 3 curves, if I took the sphere that runs along horizontal here and is punctured by these 3 things, that would be a page of my open book. And this isn't my notation, but we're going to name these things S-1, S0, and S1. That's why I can't name my surfaces S. All right. So this part so far has not been difficult. This could be an exercise in Gomp and Stipschitz, which you have to think about for a while, but we could all get through this. But there is this really cool paper from a while ago, I guess the 90s, by Price, where he studied explicitly the automorphisms of this 3-dimensional boundary. So I'm going to give it a name. This 3 manifold is called Q, which for some reason stands for quaternion space. And he showed that the automorphism group, so homeomorphisms, is just the symmetric group of order 3. So any self-homeomorphism of Q is isotopic to one which just preserves the Seifert fiber structure, but permeates the singular fibers. And you can achieve any permutation of the singular fibers. So there's exactly 6 self-homeomorphisms, including the identity. And in fact, moreover, if you look at Q as the boundary of this particular 4-manifold, the neighborhood of RP2 in a 4-manifold, then the non-trivial automorphism that exchanges these two fibers, S0 and S1, actually extends over the whole four-dimensional neighborhood. And this is the only non-trivial map that extends. Okay, so now we're four-dimensional topologists and we want to surgery out this RP2 and glue it back. Well, there's 6 choices of gluing maps. The identity clearly doesn't do anything interesting. We're going to get our four-manifold back. And now we know that this non-trivial map extends over the four-dimensional neighborhood, which means that if we choose this diffeomorphism, we could extend that to a diffeomorphism of the whole space, still get our original four-manifold. And that means that there are exactly 3 choices. So when I do surgery, X4 minus a neighborhood of F, gluing back in a neighborhood of F, all I have to do is tell you where I'm going to map this S minus 1 fiber. Can you see the blue? This one's really important. Some people do it in orange. Intuitively, I think it's like clear that if one of these circles is going to be more important than the other, it should be S minus 1, because this is actually a of my RP2, so it seems like it should contain the most information. So geometrically, this is what we're looking at. Okay. So if we map it back to itself, then we've just done the identity gluing, and we get X4. If we map to one of the other 2 fibers, 2 very different behaviors can happen. So let's say I want to map to, which one? S1, this bottom guy. So in terms of this handle structure, if I look at S1, this is the generator of all of the fundamental group in my neighborhood, right? It's going around this one handle. It represents the 2 torsion in my pi 1. If I choose to map S minus 1, which is supposed to be a generator in the complement, it's meridian, and I map it now to this thing that was previously my generator of my pi 1, intuitively, I should think that, oh, I'm mapping my relations to each other. I'm going to end up with non-trivial H1. And if I want to be more careful about it, you write down a Meyer-Via torus sequence. And when we look at this part, so if I look at H1 of the boundary of my neighborhood, mapping onto H1 of the complement plus this. When I map my meridian to a generator of the complement, that's like saying here, this map is going to map some element of 2 torsion into a 2 torsion element here, and also into a 2 torsion element here. So I get like 1, 1. But the point of this is like, I'm going to have some 2 torsion in my image, well, some 2 torsion in my range, which is like not in my image. And I'm going to end up with non-trivial 2 torsion in the next group, H1 of this new manifold, which I'll call tau. Tau F, X bar. So just by like a simple Meyer-Via torus sequence, this four-manifold has non-trivial, like different from X4, H1. So not even like homologically equivalent. But what's really weird, and this is like sort of the main theorem of Price's paper, is that this third gluing, when I map my meridian fiber to this third weird fiber, in fact, I not only preserve my homotopy group, but I actually preserve the homeomorphism type of S4 if I'm performing this operation in S4. So I'm going to write that as the theorem of Price. Erase my Meyer-Via torus. If X4 sphere, then in fact this Price-twisted, the sigma manifold, is always homeomorphic to S4. And this is extended actually a lot by, I'm going to say Akbulut and Yasui, who said that not even just S4, if we just have, for example, X4 is simply connected, and our surface is 0 in H2 with Z2 coefficients, then this is enough to tell you that the resulting manifold is homeomorphic to what you started with. But in particular, he has explicit examples where the smooth structure really does change. So he has some example where X4 is not diffeomorphic to sigma. So in particular, this example definitely isn't the fourth sphere. You probably all would have heard about it. Actually, I think it's possible that all of his examples are even non-orientable four manifolds. So I don't know for sure if we have an orientable four manifold where we know that the surgery changes the structure. But this still is an example of a surgery operation which definitely has the potential to change the smooth structure of a four manifold, and like it makes sense to perform it in S4. So it's pretty natural to study this surgery if you're interested in, for example, the four-dimensional Poincare conjecture, right? Okay, so that's some motivation for studying this. Let's talk about maybe the tau manifold. So you've probably all heard, or most of you have heard of a different morphing surgery operation called the Glut Twist. So that's a surgery that you can perform on a sphere. So one motivation for understanding this surgery in RP2 is that, in fact, in some sense, it generalizes the Glut Twist. So if I come over here, I'm not going to tell you what the Glut Twist surgery is because I don't want to talk about it. But let's just say that there is a surgery operation you can do on spheres, in particular in S4, with the potential to change the smooth structure. And it's a theorem of four people, Katanaga, I'm sorry, I just want to say their names, it's really long. Katanaga, Saiki, Teragaito, and Yamada from 98. That if you do this surgery on this two sphere, which I'm going to write as like this, really in any four manifold, this is diffeomorphic, so equivalent to doing the price twist surgery on, you take your sphere, you just connect some on, a tiny little unknotted RP2. So you make this like an RP2 in just the dumbest possible way. You do the price twist, you get the same four manifold. So if you understand the price twist, you should understand the Glut Twist. And it's possible that it contains more information, modulo some other conjecture. So there's this conjecture of Kinoshita. Technically, I think he didn't ask it, but he studied RP2s of this form. And the conjecture states that maybe, at least in S4, every RP2 is of this form. So maybe you can always take an RP2 and sort of decompose it into a knotted sphere, K2, connects on an unknotted RP2. But that's unknown. So studying this surgery operation sort of could give you a handle on answering this question. So for example, if you have an RP2, and this is a true fact about it, well then you know something about, for example, the fundamental group of our tau manifold, just by like Seifert Van Kampen. You would know that the fundamental group of the tau manifold is like the fundamental group of this 2-knot complement, maybe with an extra 2 torsion relation added in. But we know something about 2-knot groups. So that's somewhat of a restriction. Okay, so I think that's my motivation for what is surgery and why do we care about it and why we're doing a weird surgery. So now I want to talk about like how to actually perform this. So the bulk of this talk is supposed to be about trisections. Yeah, so we need a new combinatorial way to describe a four manifold. So what is the trisection? A trisection is like a generalization in 4 dimensions, what a Heegard splitting is in 3 dimensions, essentially. So a Heegard splitting of a 3-dimensional manifold is a splitting into 2 simpler pieces. We write our 3 manifold as a union of 2 handle bodies glued along the surface. Okay, so if I have a trisection of a dimension up, I take a 4 manifold, you You can't use M for a four-manifold, it's like weird. And so now my dimension up, so I'll just have one more piece, sure. And I'd write it as the union of three things, which are all simple pieces. So here in a Heegard splitting, we have a handle buddy. These handle buddies are each a boundary connect sum of solid tori, S1 times D2. When I have a Heegard splitting, I want each piece to be a boundary connect sum of S1 cross B3. So just some number of them. So that's like a four-dimensional solid torus. Maybe now we can see like kind of a fake reason why we need three pieces. In dimension 3, when you think of a Heegard splitting, you can sort of think of one handle buddy has your 0 and 1 handles, and one handle buddy has your 2 and 3 handles. But in dimension 4, you have an extra number of handles, so you need an extra piece. That's actually basically true. We have some more conditions, like here, you need the double intersection to be a surface. So here, when I look at the double intersections, this is supposed to be a three-dimensional handle buddy. I'm going to draw a picture of this in a second. And it's the triple intersection that's a surface. So like that all adds up with codimensions. Okay, so let's draw like the standard picture that everybody will always draw. So there's sort of two, one's more accurate. I'm going to draw this 2 dimensions down. So this is my closed four-dimensional manifold, which I'm drawing as a closed 2-dimensional manifold. I'm going to split it into 3 pieces, which are each 4-dimensional handle buddies. And I'm going to do that by just cutting what looks like a sphere into what looks like 3 disks. So I'll draw an arc here, an arc here. There's another arc going along the back. Whoa. Okay, and so we're 2 dimensions down. So what looks like a disk here is really a 4-dimensional ball. So I'm writing S4 is the union of 3 4-dimensional balls. Their pairwise intersections look like arcs, like an interval. I'm 2 dimensions down, so those are really 3-dimensional balls. So each one is a 3-ball in the boundary. That makes sense, because if this is like the intersection of x1 with x2, which I'm always going to say is this interval, the red interval. So let's say this is x1. Oh no, it's blue. This is x1, this is x2. Here's my third piece, x3. Then if I look at x1 intersect x2, I see a ball. If I look at x1 intersect x3, I see a different ball. And these 2 balls are gluing together to give me a Heegard splitting of the boundary of x1. Okay, so that's the situation. And then the triple intersection looks like a 0-dimensional sphere. I'm 2 dimensions down, so it's really a 2-dimensional sphere. Okay, so what's nice about these trisections is that, well, first of all, they always exist. So theorem. This is Gay Kirby, I don't know, maybe like 2005. That trisections exist for every closed 4 manifold. So that's convenient. And they're unique modulo sum stabilization operation, just like Heegard splitting. So 3 manifolds. If you have 2 Heegard splittings of the same 3 manifold, you can stabilize and destabilize an isotope, and eventually they'll be the same thing. Surface homomorphisms count as isotope. So now I want to say, like, how do I actually draw these things? Because I can't always draw everything 2 dimensions down. That makes sense for S4, but I'm going to have a hard time with CP2. So really what we should do is always draw the same data we would draw for a Heegard splitting. We're going to draw the surface that's the intersection of all of our pieces. So I always draw the triple intersection, which is a surface. So in this example, that surface is an S2. And then on that surface, I'm going to draw curves which define my three-dimensional handle bodies. So I have this three-dimensional handle body, x1 intersect x2. I'm going to say it's this one. And I'm going to, on my surface, draw some curves that specify a handle body in the normal way, right, with red curves. I would call those alphas. Well, except in this diagram, this is a genus 0 surface, and all my handle bodies are balls. So I actually have all my data right here. This is a picture of a trisection of S4. It's like the least satisfying trisection. Let's draw a slightly more interesting one. Let's say that we have, let's say we want to understand CP2. Okay, so how should you all understand CP2 anyway? Everybody should think of it as three balls glued together, a 0 handle, a 2 handle, and a 4 handle. Any algebraic geometry thing is not acceptable right now. So what I want to do is think of my 0 handle like behind the blackboard. Like, I'm looking at its three-dimensional boundary. I already have a 4-dimensional ball as my 0 handle. Okay, and then I'm going to draw in its boundary this torus. And I'm going to say that I'm gluing on my 2 handle by attaching it to this solid torus with like a +1 twist. Okay, so what do I mean? I have my double intersection between the 0 handle and the 2 handle. They're going to glue together in this solid torus that I'm looking at right now, but with a +1 twist. On the other hand, then I'm going to attach my 4 handle to my 2 handle, and they're going to glue together in some torus which I can't see, but it's going to differ by +1 framing from this one. And then finally, my 0 handle and my 4 handle are in a solid torus, which is exactly this solid torus that I didn't attach anything to, right? I attached my 2 handle only here, and like the rest of this all has to get glued to the other guy. So here's the disk. It actually bounced a disk in my complement. That's kind of vague. But somehow I'm thinking of these diagrams as encoding a surgery operation. And like, if you just think about that in your head without understanding maybe like exactly what's happening, it's okay. But so this is a picture of the 4-manifold CP2. Or maybe it's CP2 bar, sometimes I mess that up. And then if I had to like say some algebraic facts about this trisection, I would say that this is a genus 1, genus of the surface. And then use this index k, 0. And this is to indicate the genus of my 4-dimensional pieces, which are B4s. So I see that if I want to tell you about a 4-manifold, I could draw any surface I wanted and triples of curves on that surface. And they just satisfy the property that any 2 pairs, like if I look at just the blue and the green, that has to be a Hegardt splitting of a connect sum of S1 cross S2s. So pairwise, each of these gives me a splitting of S3. You can check that. So this is a valid 4-manifold, and in fact it's CP2 bar. Okay, so that's probably like enough examples because we don't actually care that much about closed manifolds right now. So what's really nice, what I really like about trisections, is it gives us a new way to think about surfaces embedded in 4-manifolds. So for the very first part of this summer school, Dave Gavai taught a 2-day class on surfaces living in 4-manifolds. And we saw like 2 different ways to visualize them, by projecting onto S3 or by thinking of these band pairs. So now here's a new way to think about surfaces using trisections. So erase this. Oh. Okay, so this is a theorem of Meyer and Zupan. So they did it for surfaces in S4 in 2015. And then they extended it to surfaces just in a general 4-manifold, like last summer. I'm going to put 15, 17. And they said that if I have a surface and it's smoothly embedded in a trisected 4-manifold, then I can always isotope my surface so that in each of the thirds, it just looks like a boundary parallel collection of disks. So I'm not going to write that, I'm just going to draw a picture of it. This is a picture of the trisection of S4. I'm projecting into S3. So I'm cutting what looks like S3 into three-dimensional balls. I'm going to dimension down. So really this is a copy of B4. This double intersection is a copy of B3. It looks like a plane. It's going off to infinity. And what looks like a line or a circle is actually a copy of S2. I just lost a dimension in my projection. Okay, and so we can think about our favorite unknotted sphere sitting inside of space, sort of centered along this line. It looks kind of like that. So if I had to describe this unknotted sphere to you in terms of the trisection, what I would do is draw my three-dimensional balls. So this is like a B3, which is x1 intersect x2. And then I would just draw the intersection of my sphere with this three-dimensional piece. So this is going to be a tangle. So in this case, it's a very uninteresting tangle. If this is x1, x2, x3, each pairwise intersection just looks like one arc, one like parabola. So remember, these are tangle diagrams. This is really a three-dimensional ball, but it's just like the most boring tangle you could ask for, right? So that's like slightly more interesting and probably relevant. Let's draw my RP2 sitting inside of space. So if I draw S4 the same way, I project these balls into a dimension lower. I could draw a copy of RP2 in the following way. I'm going to have a disk in this third whose boundary looks like that. I mean, that's an unknot, right? And this is a picture of B4. So surely the unknot bounds a smooth disk into B4, even though if I try to draw it here, it's going to look kind of bad. Okay. And then in the back, this back sheet, I'm going to put the tangle like this. So if I drew them all, I have this tangle, and this tangle. See, they're in 3 dimensions, so it makes sense to have crossings. Okay? And so if we look at the union of these two guys, they also glue to make an unknot. And that's what's happening on the boundary of this bottom third. So it makes sense to have a disk sticking out in the bottom here, in this 4-dimensional ball. And then finally, like this top tangle and the one that's sitting in the back, if we glue them together, we get another diagram of the unknot. So we could still have a disk with that boundary sticking out into this 4-dimensional ball. So I've completely described to you a surface that's made of 3 disks. So Euler characteristic 3 minus, it's glued together, well, there's 2 arcs times 3, so it's glued together along 6 arcs. And then, well, really, when I glue it together along these arcs, I also have to fill in these disks. There's 4 points of intersection in the triple intersection. So I ended up with a surface whose Euler characteristic is 1. So we can all agree that it's an RP2. And in fact, it's the RP2 with Euler number -2. Okay. But even though it's hard to finish the rest of this picture, this is very easy to draw. Okay, and then in general, like, these diagrams can be complicated, and we understand how to produce them, like, relatively well. But I'm not going to get, like, too much into that. But this is really interesting, understanding surfaces this way. Okay, so now we have this combinatorial description of 4 manifolds, and we have a way to also combinatorially describe surfaces living in those 4 manifolds from that, and in particular this RP2, and we want to understand how to do surgery on the RP2 from that. And so what should our general plan be? I think it'd be a good idea to start with a 4 manifold, which is trisected. we have an RP2 in mind. So we go to the complement. It's called F. And then we just want to glue it back in to get our surgeon manifold, either tau or sigma. SX4. And at the end, we want to have a trisection description here, like actually explicitly know something about this 4-manifold. And so the way that I think that would make sense is if we had a trisection of this complement and understood a trisection of this neighborhood, and we could just glue them together to get a trisection of the finished thing, right? So I only described trisections to you of closed manifolds, but it turns out we actually understand a lot about manifolds with boundary too, although it's a little bit more complicated. So I'm going to tell you something about those. So what is a relative trisection? Of a 4-manifold with boundary. So now I'm going to take my 4-manifold, and I think just at the beginning I should probably start off with a schematic in mind. Now I'm only one dimension down. This is like a filled-in 3-dimensional ball, really a 4-dimensional ball. And I'm going to say that a relative trisection is where I cut my 4-manifold still into 3 pieces, which are each 4-dimensional handle bodies. Boundary connect sum of S1 cross B3. Okay, so I can draw that. I'm going to cut what looks like a 3-dimensional ball into 3 like thirds. Like I'm drawing this line sort of down, and then I'm taking a knife and just cutting, every 120 degrees around, cutting an apple in thirds. Oh, I went clockwise, sorry. So now, we want the double intersections exactly the same as before. They're going to be 3-dimensional handle bodies. And in this picture, so remember our 4-dimensional pieces are these thirds. The double intersection looks like this disc that's shaped like a D. Half the boundary of the disc is on my actual boundary, and half the boundary is on the interior. Okay, and now my triple intersection is a little bit weirder. My triple intersection is a surface. This looks like this line segment, but this has boundary. So my triple intersection is actually going to be a surface which has boundary, and that boundary really lives on the boundary of my 4-manifold. Okay. So before we only had closed surfaces, but other than that, this looks exactly like our description of a closed trisection. The only weird thing about relative trisections is if you're going to have a system in place to describe 4-manifolds with boundary, you better be able to glue them together, right? If you have 2 4-manifolds with homeomorphic boundaries, hopefully trisection here, you want to be able to glue them together and get a trisection on your finished thing. And so here, if this is all I say, it's not obvious I can do that. I mean, I could try, take a trisection of this 4-manifold and glue it to another one with the same boundary, and just, let my new x1 third be the union of the 2 smaller x1s in each piece. But that's like gluing together 2 handle bodies. If I just glue 2 handle bodies together in some arbitrary way, that's probably not going to be a handle body. I need to glue them together along like just a 1 skeleton, like something really special. So we have an extra gluing condition, which is sort of like the really inconvenient part of understanding anything about relative trisections. So moreover, when I have a trisection of a 4-manifold with boundary, it must be the case that when I look at the intersection of one piece with the boundary, so here, if x1 is this front third, the intersection with the boundary is like this disc that's just lying on the boundary of my apple. I need this to be a product of the double intersection with the boundary. So when I look at the double intersection, so this is x1, back here is x2. The double intersection is this red page. The double intersection with the boundary is just this red arc. And I can see that if I take this red arc times I could fill up this whole front wedge of my dimensional boundary. Okay. So really, like the shorter way that I could say this is that my trisection induces an open book on the boundary, where the pages are just the double intersections. Okay, so that's kind of technical, but it's important. So we have ways of understanding, just from a trisection diagram of a manifold with boundary, you can read off what the open book is. It's not a big mystery. It's like inconvenient, because you have to like slide a bunch of curves around. But we understand that pretty well. That's like a lot of people have thought about this. So everything about this is due to like Cash, Gay, Kirby, Pinzon, Casedo. Yeah. Okay. So now, like in the last bit, let's talk about how to actually do the surgery operation. So I'm just going to draw for you my favorite relative trisection. So I guess I should tell you about at least one or two of them. So before, I understood this surgery of CP2, surgery description of CP2, to give me somehow a trisection description of CP2. So now I'm going to take a surgery description. Where'd it go? Oh. I'm going to take a surgery description of this guy, my neighborhood, and turn it into a relative trisection. And I had to think about this for a really long time. So it's just going to be like some magic. But I'm just going to draw the picture, and then maybe we can look at it. So what's the idea? Before, when I drew the surgery, when I drew the trisection for CP2, I drew something where two of the curves looked standard, and one of them looked like the 1-1 curve. And somehow this was supposed to tell you that you're supposed to draw a two-handle with a +1 framing, and that's the manifold that you're describing. Okay, so that's a lot of words that don't really mean anything in particular. But I'm going to do the same idea here. I'm going to draw a weird Kirby diagram for that 4-manifold. Just for some reason, this Kirby diagram is more convenient. Okay, yeah. Okay, so what is this? This is still the exact same 4-manifold. I just like did some Kirby calculus to it. I like blew up and I slid. Like, let's not worry about it. But now I'm going to project my curves onto a surface in such a way that I'll actually get a trisection description of this 4-manifold, which is the neighborhood of my RP2. So I draw a surface with 3 boundary components. Somehow I think about my 1-handles as like being swallowed by these boundaries. And then I draw 2 of my sets of curves as being standard. And then somehow I project the 2 handles onto the surface. Which I think looks like this. Okay, and just because I know that this is somehow going to encode the same 4-manifold as this actually has to be a trisection description of my neighborhood. So this is like black magic right now. There's like a long explanation of this in, I don't know, probably Game Kirby's paper. It's also like in my archive thing, but I didn't think of it, I think. But like, we do understand how to do this. Okay, and I could draw like maybe another one, 2. Wow, that's not a boundary component. With 2 distinct properties. So I'm just going to draw it and then tell you why I have 2 different diagrams. Sorry, I know this is like not good form. Okay. So I told you that somehow we know what open book diagrams like this induce on the boundary. And what's really weird here is that these both have to induce open books with 3 bindings. In fact, they're both like this open book, where the bindings are my 3 singular fibers. In both of these pictures, our favorite S-1, the meridian, corresponds to this boundary. And they still have that 2, 2, minus 2 monodromy, but in different orders. So in this open book, this one gets the left-handed twists, and the other 2 bindings have right-handed twists. But in this open book, our preferred meridian gets right-handed twists. Okay, so I just think that's like super weird that we can induce like almost the same monodromy, but sort of the binding components exchanged. Okay, so now why is that useful? I have like 1/2 of the piece of the puzzle. I have a trisection description of my neighborhood. I know that I want to be able to glue it to a trisection of my complement. In order to be able to glue, I have to induce an open book. And I guess I should have said that in order to be compatible, I can only glue it to things that have the same open book, opposite orientation. That's sort of like the compatibility criteria. So now if I take another trisection of a complement, which induces this preferred open book, the 2, 2, minus 2, well, if I use this trisection, I can glue my favorite S-1 fiber to the binding that's the odd one out. And if I use this as my description of my neighborhood, I could glue it to either of the 2 other ones. So if I have a trisection description of my complement, then using either of these 2 diagrams, I can achieve any 3 gluings of the RP2 back into the 4-manifold. Okay, so I wanted to tell you about how to actually get the trisection description of the complement, because that's sort of like actually like most of the length of like what I thought about, but it's also the thing that's really hard to explain, and I thought like, I don't know. But I'm going to give you like the general idea really quickly. So let me erase this. So we came up with this procedure. This is all joint, I should have said that at the beginning, but this is all joint with Seungwon Kim, who's at the National Institute of Mathematical Sciences in South Korea. Given a 4-manifold, it doesn't have to be an RP2, it doesn't have to have any particular Euler number, and it can live in any 4-manifold. It doesn't have to be S4. From a description of a surface like this, these like pictures of tangles, we can output a trisection of its complement, or relative trisection of its complement. Okay. So for spheres, if F is a sphere, this was already understood by Meyer and Gay. So I guess it's Gay first, alphabetically. So they understood how to get complements of spheres as trisections because they were understanding how to do sphere surgery. So Jeff Meyer and David Gay recently posted a paper where they illustrate using trisections how to perform the Glut Twist, surgery on S2 where you delete S2 cross D2 and glue in like S1 cross D3. And then I think some other more complicated quadratic surgery on spheres with Euler number 4. But for the general case, something like more complicated happens. So when your surface is you can just take your trisection and essentially just delete the intersection of each piece with the sphere, and you're just going to get, for free, a relative trisection on the complement. And something weird happens when you have any other Euler characteristic. So I mean, if you're really interested in it, we can talk about it later. But I think I'm just going to say that like it's not trivial when your surface is a sphere. When your surface is not a sphere. Okay, but in particular, something nice happens. In particular, if the surface is an RP2, you can always do this so that the trisection you get at the end, that open book that it induces on the boundary, is planar with 3 bounding components. So open book page It's just like the disk with 2 punctures. So what's nice about this is from a trisection, it's actually pretty easy to read off like the topology of the page. Like I can like instantly tell you the genus and the number of boundary components. What's hard is like understanding what the monodromy is. But the mapping class group of this particular surface is really simple, right? It's generated by Dane twists around the 3 binding components, around like disjoint. So I could just easily write down the fundamental group of this thing. If I twist like here A times, here B times, and here C times. Those are trisection colors, but it's not a trisection. Those are just circles. The only way that I can get the right fundamental group of what I know has to be my boundary is if these 3 numbers of twists are all 2, 2, minus 2, up to sign. They all have to be 2, 2 of one sign, 2 of the other. Right. And then I just know because like I have to be inducing the opposite orientation on my 4 manifold for free. It has to be that the opposite of my one from my neighborhood. So my neighborhood and my complement, just for free, have the same monodromy induced with opposite orientation. And that tells me that they're going to be compatible to Glut. Okay, so in the last few minutes, I thought that I should show you an example. And I wanted to show you an example that wasn't like the most trivial thing. So I picked the second most trivial thing. But it turns out that the complexity blows up kind of fast. Okay, so this is a picture. What's going on here? I'm drawing 3 tangles, right? They each live in the 3-dimensional balls, which are the sections of our trisection. I drew them slightly more complicated than before. And you could check, I didn't draw them like paired up, but if you glued this tangle to the mirror of this one, they would actually become a 2-component unlink. And same thing for the other 2 pairs. If you glue them, mirror image, you're going to get a 2-component unlink. So what I've drawn for you is a surface that's cut into 6 disks, with 2 in each third. And it's glued together along 5 times 3 arcs. So the Euler characteristic is 6 minus 15, plus I have to cap off each of these intersections with a triple surface, 1, 2, 3, 4, 5, 10. So this is the surface of the Euler characteristic 1. It's definitely an RP2. In fact, it has a cute name. It's called the spun trefoil connects on the unknotted RP2. So there's some combinatorial procedure, which is, it's not random, like you can actually just do it. Somehow we stabilize our underlying trisection. Right now it's 4 balls, 3 4-dimensional balls glued together, and I stabilize it a bunch of times. I take a tube, which right now lies in x1 intersect x3, and I just declare like now this tube belongs to x2. I increase its genus by 1. And I do that so that now after I've stabilized a bunch of times, my surface actually intersects each of my thirds in a single disk. And then I delete the surface, and I have to play some game to fix the boundary condition of my 4 manifold. So this is like the thing that I didn't have time enough to talk about. But somehow I have to actually ensure that I have an open book induced on my boundary. And I can do that. It's just that I might have to take arcs that lie in the boundary of the complement. And right now maybe this arc lies in x1 intersect x3, and just declare that its neighborhood, which looks like half a ball times an interval, is going to lie in x2. And when I do that, I actually have, at least in words, a relative trisection of the complement. Well, that's not helpful. I have to actually be able to draw curves on a surface. Okay, so I draw the triple intersection. So the triple intersection was a sphere, but I stabilized by adding tubes into each of my 3 pieces. So now it's this genus 3 surface. And then I delete the intersection with my RP2. It intersected in 4 points. And then something weird happens when I take arcs that lie in the boundary, and I just shove them into like the 3rd piece, where I add bands to my triple intersection. So that's not so important, but there's something weird that happens. And then it's actually really straightforward to draw the curves. It's just like not the most fun thing. But for example, if I look at x1 intersect x2, well, I know that I have this arc, which I could project down to my surface, and it would look like an arc that sort of started at this point and wrapped around the back and around the front and came down here. And I could take a disk that sort of swallowed that arc, so it follows this path, and it just comes vertically up and encases the arc. Like, think about Beauty and the Beast. You got the rose, you got the thing over it. It's like that kind of thing. Okay, so that's what this curve is, right? It's like, shoop. Yeah. So you just project them all down, you draw curves around them. I'm not crazy, so like, I would prefer to have the boundary be simple, like circles. That's much better, right? Okay, so now we're ready to actually get our description of the surgeon manifold. So it's not too hard to check, although I didn't tell you how. Then in fact, if I look at the monodrome induced by this open book, I swear it's actually not that hard to check. That the twists are, the right-handed twist is around this boundary, and it's left around these two. So now I go to glue. Well, this is supposed to be a meridian. So if I glue the meridian back, then like, surely I just get my original four-manifold X4. So this is the four sphere. On the other hand, this curve bounds a disk in this picture, exercise, and if I glue my meridian to that curve, I'm going to get non-trivial first homology. So this must be my tau manifold. And then finally, if I glue my meridian to the third boundary component, just by process of elimination, that has to be the price twist. Okay. That's my explicit trisection description of the price twisted manifold. It's a homotopy four sphere. It's the real four sphere. I would have like had a much different title. Okay, so that's sort of like a future potential direction of this. I mean, even if we happen to know that this is actually the four-dimensional sphere that we're describing, I mean, I think like, let's not try to shoot like too crazy, right? Like probably that's four. There's sort of this weird thing of big difference between trisections and Heegard splittings, which are Heegard splittings of S3 are very simple. We have Waldhausen's theorem, which says that every Heegard splitting of S3 could be destabilized to like the trivial diagram. And that's just not known to be true for sections. We don't know if every trisection of S4 can be destabilized down to the trivial diagram. And in particular, Alex Zupan at Nebraska has been thinking about this for a long time. There's a lot of proposed like weird trisections of S4, which people think are probably not stabilized, but it's really hard to determine if that's true, because you can't just check every possible surface automorphism. So this is my proposed probably not stabilized diagram of S4. So I don't know how to check that yet. Yeah, and then I guess the other thing in the future is, so I only really talked about RP2, but I did tell you that we know how to trisect the complement of any surface in a four-manifold. So in particular, now we're trying to understand how to trisect the complement of like the regular fiber of a Lefschetz vibration. So instead of doing surgery, we could think of the slowing as being like doing a fiber sum of Lefschetz vibrations with boundary. Yeah, and that's sort of the next direction. So I guess I'll stop there. It's like an hour. Oh, yeah.
Did you get that like a proposal?
Doing the surgery, the way that you would do the surgery and then think that you couldn't decompose it would be if you did the surgery and couldn't decompose the surgery as like a connect sum. But I think that that would probably not be easier than finding the surface like already as a connect sum in the Tingle description. So there's some attempt at enumerating surfaces based on these braids, like, but it's very small. That's sort of like the only thing that's potentially like that.